Good afternoon, everyone. Welcome to the webinar on natural gas hydrate. I take this opportunity to welcome today's expert, Mr. Bhavik Mahant. He has completed BTech in Chemical Engineering, MS from IIT Madras, and now he is pursuing PhD from IIT Madras. Sir has worked in UPL as a process engineer. International, one national, and five conference. It is an honor and privilege for us to have you, sir, today. Now I am handing over the session to you, sir. Sir, please.
I'm Bhavik Mahant. So actually today is day for us, for everyone, for all every Indian, because today is the 15th October and it is the birth anniversary of Mr. Dr. APJ Abdul Kalam. So I am very much honored for for from Parvi University to inviting me on this precious day. So we will start our webinar. My topic is nature gas hydrate and unconventional energy resources. So basically, this is the outline of my webinar. We will start from the introduction and then we will get into a little bit of history of what is the gas hydrate and how can we extract the nature gas out of it. Then we go for the how we will proceed for nature gas production out of it. Then techniques for that. But because of this is a in the fundamental part, so we have to do some lab scale research for the gas hydrate. Then there are what are the major challenges are there, and we have to do economic evaluation also. So let's start with the webinar. So this is the slide in which you can see that global primary energy consumption by sources. Here you can see that from 1860 to 2000, you can see starting from the coal and we have went up to the renewables. So basically day by day, all the countries are like, skipping onto the coal and jumping into the oil as well as natural gas, and shale gas boom is happened in the America also. So you can see that we are very much dominant in coal. After that we will go for oil and gas. In India, all the thermal power stations are still working on the coal only, but we have to change our priorities with the time. So government also started some natural gas based power plant. So what is the benefit of that? So main benefit is it is a decarbonization. As you all know that from coal, there is so much amount of pollution we did into the atmosphere because if we use if we use coal as an energy source, then for per gigajoule of energy we have to spend 27 kilogram of carbon dioxide into the atmosphere. Then we switch over to oil, and then we now it's around natural gas. You all know that we have power. Natural gas is in our daily use also as well as industrial use also. It is almost half of the call is it creates the pollution almost half of the call, but still we will go into the hydrogen in the future generation. But it is hydrogen has its own problems, its own challenges. So basically nature gas is the promising source of an energy till now and in the future also. So you can see that current world energy scenario is what everyone tells about. You also heard that petrol is going to extinct in another 60, 70 years, maybe 100 years. Coal is going to extinct in 15 to 50 to 60 years. So why? Because we here you can see that in coal, majorly all 29% of global energy consumption is come from the coal only, and we have only 749 billion tons remaining coals. As well as if you go for oil also, then also you can see that only 239.4 thousand million tons of oil is there, and natural gas is only this is all the conventional natural gas. We have natural gases in unconventional form also, like we have shale gases also, we have oil sand, coal bed methane also. But if we talk about the conventional natural gas, then it is only 186.9%. So 9 trillion cubic meters. So we can say that next after next 60 to 70 years, there will be no conventional fuel of coal, oil, and natural gas will be there. So what is the solution afterwards? What can we do? So now let's start with the natural gas hydrate. What is it? Basically, I think it's a new thing for everyone. Maybe you guys also not heard about much on natural gas hydrate. In chemistry, there are two types of hydrates for there. First is a basic hydrate, which is made hydrate from metal compounds like iron hydroxide has hydrate something, magnesium oxide has hydrate. So it is a different types of hydrate. It has some chemical bonding in between. But here we talk about the natural gas hydrate, or it is also known as a clatrate hydrate. Why? Here you can see that water makes an structure which is cage like structure, and which is a help with the help of hydrogen bonding only. And in this cage like structure, gas is encapsulated, or gas is fixed in between the this cage like structure when at high pressure and low temperature. So you can consider that it is only physical bonding, not the chemical bonding. So we can easily break this bonding, because you can see we have water and gas, any gas. It's not only methane or carbon dioxide. We can make gas hydrate from any gases. So when low molecular weight gas combined with water and freezes into solid under low temperature and a moderate pressure, then it is known as a natural gas hydrate, or we make known as a clatrate hydrate. So here you can see that it's also known as a burning hydrate, which is an when natural gas, which is methane, if we burn that hydrate, we will lit the fire to that hydrate, then it is burning like it is fire coming from the ice. So it is also known as a burning hydrate. And what is the main property of natural gas hydrate? It is here. If we have 1 meter cube of hydrate, which is composed of water and gas, then it has 0.90 meter cube of water and 164 meter cube of gas. You can imagine this is the uh, vast amount of gas which is encapsulated into the small amount of hydrate. So we can store gas also. And in beneath the earth or below the sea, there is a natural gas hydrate sources are available. We can extract natural gas out of it also. How we can do? We will discuss in a further slides. So here it is the same thing, hydrate forming condition. What are the forming condition? As I tell you that it consists low temperature, high pressure, and mostly liquid water must be there, and any small gas molecule will be there. It can form a gas hydrate. Here you can see that it is a gas water molecule which is in the form of cage like structure. It is a cage. In between you can see a small gas molecule will be there, and all the bonds are hydrogen bond only. In this hydrate equilibrium come, you can see that if you want, it is different for every gas. Let's say it is here it's this for the, if we consider it is for the methane, then if we talk about the carbon dioxide, then this curve may be like this or maybe like this. It depends on each and every individual component. So what can be derived from this curve? If you can, is a basic thing. If you want to form the gas hydrate, then if you consider this 63 or 64 degree Fahrenheit, then the pressure will be which is needed. It's around 2500 to 2400 psi. So it is basically indicates the how much pressure and temperature required for making a gas hydrate. And you can also consider one thing: if you want to make gas hydrate at this particular temperature, then if your or you can say that this temperature, this particular pressure, then if your temperature is higher than 60, then you cannot make a gas hydrate from it, or you cannot find gas hydrate at this area. Or if your temperature is below than this, then you can find the gas hydrate. So this is only basic hydrate equilibrium curve. From that we can find that what is the physical condition required for making a gas hydrate. Now, there are the types of gas hydrate. So basically, there are more than 20 plus different types of structure are exist. But most importantly, there are three structures which is very much useful. So you can see that here the small blue ball is there. It is made out of 20 H2O molecule combined with each other, and it is known as a 512 cage or small cage. 512 means here you can see that 12 pentagon are there. 12 pentagon are combined with each other and made this cage. Same, this is also this is known as a large cage. In large cage, you can see that 12 pentagon and 2 hexagon. These two are combined with each other and made structure 1. And in structure 1 hydrate, totals 46 H2O will be used, and this is the what it looks like. So it is totally cage like structure only. If you talk about structure 2, then the same small cage and the another large cage which had 12 pentagon and 4 hexagon are combined with each other and make structure 2 hydrate. Same, this is a structure H, which is very useful because it consists not only gas molecule but also liquid organic material molecule also. So here you can see that it consists of 3 512 plus 2 this medium cage. You can say that this is a medium cage. In here 3 square, 6 pentagon and 3 hexagon are there, and this is the largest cage, 12 pentagon and 8 hexagon. In here 136 H2O will be combined with each other and made structure. So this is how it is look like. You cannot see by without any sophisticated equipment, but you can interpret as after getting the result, it is exactly look like this only. So all the three structures have mostly H2O in it, and then what are 15 more percent, another 15 more percent are gas like any gas molecule. So basically, we talk about the methane, ethane, any carbon, any hydrate which is consists of structure 1 only. So go to the next slide. Here you can see that this is the list of compound. Which compound make which type of structure. So in structure 2, you can see that hydrogen, small molecule, nitrogen, oxygen, argon are made of structure 2 hydrate, and that too in small cages are majorly they are encapsulated in the small cages only. While if you talk about methane, ethane or carbon dioxide, basically main is the research of interest of gas hydrate are the methane and carbon dioxide. They form the structure 1. This is the radius of that structure, atomic radius you can say 5 angstrom. And again structure 2. Why there are 2 times structure 2? Because these hydrogen, oxygen, nitrogens are used for small cases of this structure 2. But if you want to fill large cases of structure 2, then you have to go for propane, isobutane. These are compound, these gases are go for the large cases of structure 2. And if you talk about the structure H, then you can see that here there are organic material also. Means these are organic liquid. Dimethyl butane or cyclopentane. These are organic liquid. Liquid can also form gas hydrate. So it's also so many application on chemical perspective also, not only just nature gas or nature gas storage. And here you see some simulation based of example of gas hydrate. Here it's every molecule are always in a vibration only. You can see for any compound. But after the whole, if it is for a structure 1 gas hydrate, you can see the small gas molecule in between, and all the gas different types of molecules combined with each other and made one biggest structure. And here you can see it as ice-like structure. It is the methane gas hydrate or natural gas hydrate. If you light the fire, then it can lit also. It is basically purely made out of water and methane. Now we have to talk about little bit history. I am trying to go as much understanding. Everyone can easily understand this thing. So I am only just involve that many thing only. So history, you can see that first time Sir Humphrey Davy, the greatest physicist and chemist in his time, what he did, he actually, you know that London has a climatic environment colder than us. So he did some experiment at that time and the night, and he put the chlorine gas in some equipment or anything, and because of temperature, low temperature, that chlorine is converted into the gas hydrate at the first time. Then he mentioned in the research that the solution of oxymuriatic gas in water freezes more readily than pure water. He didn't understand that what happened first time. No one can understand what is happened. So he told that it is freezes more readily than pure water. Means he trying to go oxymuriatic means chlorine. Okay, he trying to say that chlorine is also makes chlorine is also freeze. So this is the first encounter of gas hydrate. And second, whatever that happened in 1811, after 12 years, Michael Faraday actually did the same thing, and he confirmed that it is the chlorine hydrate only. He didn't know that what should we call it, but he called it chlorine into 10H2. So this is how people should know about people did experience with gas hydrate. After that, these are the milestones in this research. If you talk about 1820 to 1934, in these 111 years, no one knows that how can we do this or how can we use this nature gas hydrate or any gas hydrate. After 1934, when nature gas boom was happened at that time, all the people were shifted from gas oil to nature gas. At that time, first time Norway encountered one problem, that nature gas, because of low temperature, freezing and converted into a solid form, and it is plugging into the gas pipeline. So 1934, the first research from Norway was done. After that, still 1965, no one knows that gas hydrate we have in our earth also. After conventional gas, oil and gas, we also have nature gas hydrate in our earth or beneath our sea also. So 1965, people might get to know that this is the thing. After that, 1999 to 2003, the first time, but we know that we have to dig the well for getting oil and nature gas from the earth surface. So same thing, first time in Canada, uh, well was dug for the natural gas, and 1150-meter deep hydrate research and production well completed in 2003 at the Malik site. After that, 2008, the first time production was done from that well. And India is also part of this research. We have to proud of that thing. After that, at 2010, same thing was done at Alaska by USA. After that, Japan came into the picture 2012. It also did some testing, and at the end, China is started its testing in 2016, 15, and 17. It full-fledged research on production testing is done in the South China Sea. Chinese people are, whatever you think that or criticize that, they are most innovative and most research based, actually you can say, persons, because most number of patents in any area, the patent are filed by Chinese people only. So now we can, you know that gas hydrate is the thing which we can found, which we can make also from lab, and which we found in beneath the earth also. But what are the exact applications of gas hydrate? What are the future characteristics which we can derive from the gas hydrate? So first is, you can see that it is easily get fire, means we can use as a fuel, because by after extracting the methane out of it. So that is known as a nature gas production out of gas hydrate. First and foremost thing is CO2 sequestration. We all know that pollution is too much in our environment nowadays. So everyone knows there is so much climate change is happen, global warming is happen. So what we want to do, we want to do carbon capture. So how we capture the carbon actually? In India, no one is starting to doing that, but in foreign, some countries started to do carbon capture. How they actually from industry, in India majorly everyone, or industry or power station, all the stakeholders are basically liberate this carbon into the atmosphere only. But in the outside world, they they separate this carbon dioxide and they actually absorb in adsorbent as well as absorber. So many different technology they actually they develop. We can do this with the help of gas hydrate also, because carbon dioxide is a gas. We have water, plenty of amount of water. We can sequester carbon dioxide beneath the sea also if we apply the pressure. So this is the very good application of gas hydrate. Second thing, nature gas storage and transportation. As we know, at now, nature gas will be transported by liquefied nature gas only. We can shift into the solidified nature gas by using a gas hydrate technique. We can pressurize gas at low temperature, it will convert into the solid, and we can transport it solid also. I will discuss in more in later slides. Then we can store hydrogen also. This is the major advantage, because hydrogen is the future of all the fuel and energy sector. But we cannot use hydrogen now because it is, you all you know this, because it first thing is it is very flammable. And the second thing is we can it is if we go for liquefaction, then it requires too much amount of economical burden over it. We can treat water or desalination also, because we have water with contamination. If we convert into the gas hydrate, then we can extract it out pure water. We can do gas separation also. There are two gas, and we can make one out of it as a gas hydrate, and we can use it for the gas separation also. These are the major application. So we have started with problems in the gas hydrate industry, how we come to know, and what are the research going on in the different types of sector. So basically this is for a flow assurance. As we know that everyone is using natural gas in maybe in Vadodara also. Everyone has a gas pipeline in their kitchen. So it comes from Alaska, majorly Alaska, Qatar, in shipping, and after it coming to the Dahej terminal, it came to our house at a piping. So there might be chances in foreign countries temperature is very much low. There might be chances it can convert into the solid, and it can be basically plugged into the pipeline. So this is, I know, I told that the first encounter of gas hydrate in pipeline by Norway. After that, they found that gas hydrate, if stuck into the pipeline, it either break the pipeline, or it can be end up to the bursting also. So it is a major loss of industries. So what can they do for preventing this gas hydrate plugging? So this is a old research. In 2002, some person told that if you want to reduce the or prevent the gas hydrate to form in our pipeline, then we have to add methanol into it. Yet you can see it. If you can't able to see, then I will explain it. Not an issue. Here is a offshore facility for natural gas production, and here is an onshore facility. If the distance between these two is 5 miles or 10 miles, then we don't need to go add methanol into it. Then it is not forming gas hydrate. But if it is more than that, 25 miles or 30 miles, then we have to add 30% methanol into our natural gas, so it cannot form gas hydrate. So this is a research, and nowadays all the industries use methanol while transporting natural gas into one to another place, as well as they also use some chemical additives also. If you go same, if you increase the distance like for 45 miles, then you have to add less amount of methanol. This is the basic research for the gas hydrate for flow assurance. Uh, Now this is some data for CO2 capture, and this research is going on IIT Madras basically, and say many other places, but in India, majorly ONGC and GAIL funded this research in the IIT Madras. In here you can say that this is the picture of which is in the lab. You before also you see it, you saw this picture. In this picture you can see it. It is a gas hydrate we form in the small reactor. We add carbon dioxide and water into it, and then we pressurize the reactor, and we lower down the temperature. Then it convert into the gas hydrate. So this is a CO2 gas hydrate. What is it used? So as I know that CO2 capture and sequestration is useful for upcoming future, because global warming and climate change is a major issue for everyone in future also. So here you can see that this is the power plant. From power plant, if we extract the carbon dioxide and we can convert into the gas hydrate, and then if we can store it into the silica sand bed or beneath the sea beneath the sea layer. So it is a very useful technique. If we can store CO2, or we can capture CO2 and store in beneath the sea, so it is not responsible for global warming after that. And the major research is going on in our community or in our college also, that we all know that we have natural gas in the form of gas hydrate under the sea. How can we extract the gas, natural gas out of it? If we can inject carbon dioxide into the natural gas hydrate area under the sea or under the anywhere, then carbon dioxide will replace the methane, and methane will be extracted out. So it is the best method. We can at the in the it is like you can kill two birds in a one with a one stone. You will we will capture the carbon dioxide also, and you will get the methane also. Why this happen? Because theoretically carbon dioxide gas hydrate will be more stable than methane gas hydrate. So it is useful for replacing the methane gas hydrate. So this is one research. We go up to the gas hydrate for energy storage. So here you can see that it is a, I am doing the research in this area. Basically, you all know that we have to go for minus 162 degrees Celsius for liquefaction of natural gas, and then we can transport it. But what are the pros and cons? We can discuss here. Here you can see that liquid hydrogen, gas hydrate, CNG and LNG. How much energy density is there? Energy density is, if you have 1 liter of CNG or 1 liter of LNG, then how much megajoule of energy we can produce out of it? You can see that gas hydrate is comparable with liquid hydrogen and CNG, but LNG is way ahead of it. But if okay, so we can say that LNG is the best option over here. But if we go and talk about the operating condition, this graph indicates the operating condition. If we go for LNG, then here you can see that we have to go for 111 Kelvin, or and pressure is 0.25. So for achieving this, we need to spend so much money into it. At the same time, if we go for liquefaction of hydrogen, then also 20 Kelvin means minus 253 degrees Celsius. It is the major commitment. We have to invest large amount of money for that. And then also liquefaction of hydrogen, it's not that much effective in some countries. So these two are very much economically more creates burden of every technology. Then if we go about CNG, then for CNG we have to pressurize the gas, natural gas, up to 200 bar, and it is also somewhat of more require more money than basic methods like oil. So what can we do for gas hydrate or for natural gas? So these are the two examples, and this is the gas hydrate of methane, which can be produced at 295 Kelvin, or you can say that 22 degrees Celsius. At 22 degrees Celsius, we can produce gas hydrate of methane. So it is approximately almost room temperature. We don't want to invest so much money into it. And the second thing is pressure is 50 bar only. So it is also achievable with low money. If we in future it is requirement for methane and hydrogen storage in the form of gas hydrate, then also 277 Kelvin means it's a nearly 4 degrees Celsius. We can easily achieve this thing, and pressure is also not that much. So gas hydrate is the one technology which we can use for the storage of energy and transportation of energy. Solid we can easily transport than liquid or gas. So this is the best technology which we might be used in the future if we go like that. Okay. Now this is the gas hydrate for gas separation. This is a simple thing. I don't want to go for much detail. You have two gases with you. If you want to separate it out, you have to you give some pressure and temperature. Yeah, so one of it will make the gas hydrate, and another we can separate it out easily. So here you real life example. This is also nitrogen and CHF3. And for you can also we also know that in power plant flue gases were there, which consist nitrogen as well as carbon dioxide, and we want to separate carbon dioxide out of it because carbon capture and all these things. So you know that you can see that for carbon dioxide gas hydrate, the temperature is if you go for 274 temperature, then roughly 2 to 3 megapascal is required. And for nitrogen, for converting into gas hydrate, it requires more than 15, 16 megapascal. So if we for flue gas, if we give the temperature pressure condition near to this 274 and 2 megapascal, then CO2 will be converted into the gas hydrate and we will easily separate out the nitrogen. Okay, so till now we saw the different application of gas hydrate and introduction and all these things. But what is important for you guys? You are the petroleum and engineering guys or petroleum guys. So you have to more focus into how can we produce nature gas out of gas hydrate. So for you, here are the two basic figure are there, and there you can see that this is a permafrost. Permafrost is the onshore, or you can say the near to water, but it is on the in the land zone. If you want to go for land zone, the gas hydrate will be around 200 to 700 meter deep, depth in depth. If you want to extract it out gas hydrate, then you have to go for this much. And if you talk about ocean, beneath the ocean, this is also no also can you can say that marine environment in your if you go for hydrate in marine environment, then you have to go for 3,000, 4,000, 5,000 meter. It is very much beneath the earth. Basically oil and all other are less than or 1,500 or 1,000 meter only. So it is the beneath the earth, but the large amount of gas hydrate in the marine environment only, not in the this permafrost environment. So we have to go for that. So this is a little bit the same thing which I discussed in the last slide, that if you go for marine environment, then methane hydrate, gas hydrate stability zone. Stability zone is the zone you can in which at the required pressure and temperature it is present in the hydrate. So basically this is the phase boundary, or you can consider that if your pressure is 400, sorry, it is the height depth. If your depth is 400, then you have to go for almost 3-4 degrees Celsius temperature, then your gas will be converted into the gas hydrate. Uh, if your depth is 200, then you have to go for minus 20 degree, minus 15 degrees Celsius. So and pressure is already created by this amount of water. If you go to down 1200 meter, then there is a tremendous amount of pressure which is there because of this water above. Then you have to made where you found gas hydrate at 15, 16, 17 degree also. Same this is for permafrost means onshore. Onshore you can find gas hydrate below between 200 to 1,000 meter, and that too at around minus 20 to 15 degrees Celsius. I just want to tell you these things. Just don't go much detail. It is for information only. Now, okay, don't afraid of this big diagram. I just want to tell you the recent figures and recent or means which is in last 10 to 20 years. What are the figures or their actual figures? Here is the 2006 research. The topmost red section is the conventional oil and gas, which we now extracted, which are we extracting now. So this is only 13 TCMs only, trillion cubic meter. After that, US started tight gas and shallow gas cells or cell gas on CBM, coal-bed methane. So it consists this much amount, largely 330 TCM. But for getting that cell gas, you have to invest so much into technology, and then also you will get something. But if you talk about methane hydrates, at how much amount of methane hydrates are our Mother Earth have, then it is a 3,000 TCMs, more than all of this. We have tremendous amount of methane hydrates with us. So if someone tell that CNG and natural gas will be extinct in nearby future, then you can show this type of figure and you can tell them that we have maximum amount of our resources for energy storage, and we can use it up to the 200 300 more years. These are the different types of sands and different types of land where these 3000 tcms are available. So they already predicted that after 2030 we will use this methane hydrate, but it is we will see in future that we can do it. Okay, and in this diagram, please don't afraid. I just want to I was just want to show you some images out of it. That if you, this blue line is gas hydrate stability boundary line. If you go for AB section, means if you found beneath the water, if you found the gas hydrate, then it is look like this A and B, this type of gas hydrate. If you go for C section, 200 to 1000 meters beneath below the sea, then you can find this type of gas hydrate. These are the rare pictures of gas hydrate. If you go for the sea floor and then somewhere you find the gas hydrate, then it is like this. If you go for the E section, then this like this only. And this is the permafrost, means below the land you will find this type of gas hydrate. I just want to tell you the figure of it, nothing else. Okay, thanks. Okay, so this is the country wise or worldwide availability of the gas hydrate. You can say that it is evenly distributed in all around the world. We are very much blessed, so we have some amount of gas hydrate with us. So we can in future we can be independent in energy storage and energy fuel and anything. So we can use this gas hydrate also. So you can see that everywhere there will be a gas hydrate. We can extract from everywhere. Okay. Okay, so this is the actually important side for research for actually application purpose of gas hydrate, or you can say that real time application means this is the slide which indicate that what are the things happen till now. So you can start from this. This is a Malik. It's in a Malik is a site name. It is in Canada, and these are the countries and organizations which dug the well, and they produce the gas hydrate, natural gas out of gas hydrate. This is the first one. After that, so many countries are doing their own programs. Alaska, US use North Slope, and you can also one thing also that. I found the pictures of Malik site also. This is the how the gas hydrate from Malik is look like. Then this is a for Mount Albert at 2007. It's also how it is look like. And this is a KG basin, Krishna Godavari basin, India. So here you can see that in India you find ONGC, USGS, and DGH. They are starting two NGHP 1 and 2 program. NGHP means National Gas Hydrate Program 1. One is from 2006 to 2016 and 2 is 2016 to 26. 2 is going on now. They found some sample out of it and they did the research over there. Same, this is for all around the world. Okay. And this is the time when after NGHP 1, NGHP1, ONGC and everyone announced that India has close to 2000 trillion cubic meter of methane. So worldwide there is a 20,500 trillion cubic of methane is there in the form of natural gas hydrate. For most important thing is the form of natural gas hydrate, 20,500. If we use 15% of it out of it, then it is we can use it for all the world energy need for 200 years. And if we talk about India, then if we have 2000 TCM of methane, which is actually 1500 times more. Now we have natural gas reserve in Bombay High and somewhere. So 2000 is 15 times more than this. So if we can extract the natural gas hydrate, then we can independent of all the energy resources for next 200 years. So this is the major breakthrough. So at that time, in the same time, you can see July 26 papers, everyone newspaper you find everyone India find the gas hydrate. So this is the very great news for all of us. So the same thing where we can find in the gas hydrate in India. So here you can see it is the KG basin, Krishna Godavari basin, Mahanadi basin. There is somewhere here in the Konkan basin, and Andaman and Island is also there. So all four places we found nearly about 2000 trillion cubic meter of we have actually we estimate the thing, we estimate that this much amount of natural gas hydrate were there. If we can extract 10-20%, then also it is very much beneficial for humankind. Okay, so this is a basically roughly theoretical data that after this nature gas hydrate research is going on, they propose a classification also for this nature gas hydrate, which we found below the earth or beneath the sea. There are basically four classes. First class in consists highly saturated deposits, means it consists only methane into it. Then we have deposit underlying mobile gases and mobile fluid. So which consists gases and fluid below them. Then there is no mobile fluid, and four is the permafrost associated and marine deposit that are poorly saturated and occur with sediments. So basically they consist so much sand, so much mud and all these things, and less amount of gas added into it. So these are basically classification theoretical data. From this you can find that how much your location is, how which type of gas added. Now nature gas added is a hazard. What we if can't able to extract this gas hydrate, then you can see that we are still now we are doing the gas natural gas production from this well kind of structure, and for enhanced oil recovery we use steam and all these things. So whatever the heat will be produced from this steam, that will affect our natural gas hydrate, what you call storage also, in whatever the storage we have in our earth. So if this heat will be reached to the that storage, then basically this natural gas hydrate will be dissociated, because lower temperature only methane will be encapsulated, higher temperature it will dissociated and convert into the methane and water. Then basically all the things will be collapsed down. It is a one problem, and the second problem is all the methane will be coming out to the and into the sea. All the aquatic life will be in danger. And the second thing, methane will be going to the atmosphere. So you know that carbon dioxide has a global warming some potential, but methane has 24 times more than carbon dioxide. So it is where you can imagine that how much amount of methane will be released into the atmosphere, and what is the temperature of Earth after it. So we have to take consideration of this as a hazard also. So how can we use if how can we extract gas nature gas out of gas hydrate? So here you can see that this is the pressure, and this is the depth in water depth below the sea. So if 2000 meter is there is some gas hydrate storage is there, how can we extract natural gas out of it? So here 200 atmosphere pressure is there, and some 10 degrees Celsius temperature is there. So if we want to break this gas hydrate into the methane gas and water, then we have to heat it, so it can come up to the 20 degree, so it can come to water and methane gas. This is the one way. The second way is we have to depressurize it, means we have to apply vacuum out of it from the earth surface, so it will went up, well, it will go from 200 to 15, and it will convert it into the methane gas and water. These are the two techniques. So how we can extract the natural gas from gas hydrate. So this is the same thing. This is a hydrate formation curve. If you want to convert it into methane gas and water, then you have to go for increasing temperature, and then you have to cross to this hydrate dissociation curve. After that only hydrate will be dissociated into water. The same thing also. Okay. So this is the techniques exploitation for the gas hydrate. So these are the techniques applied also in Malik's and other locations. So this is a thermostimulation. We have to add some heated fluids in the at the where the storage of gas hydrate will be there. It will be dissociated, into the water and gas, methane gas, then we will extract gas out. This is the one way, but it consists because depth is so much, so we have to pay so much money for doing this. So now economical method is we have to go for depressurization. In depressurization we have to apply vacuum or anything like that, then gas from so pressure will be reduced over here, so gas hydrate will be converted into the gas and water, so we will extract gas out of it, and also we will get water also as well as sand also, but we there is also one problem for using this thing. So whatever water we got out of it we will recycle to sea, but whatever the sand we get out of it, it is the major issue at this stage. And this is third technique is additive injection. You have to add some chemical out into that it will decompose the gas into gas added into gas and water, and then we can extract gas out, but it is very risky, and environment protection agency don't want to go for this because chemicals are always riskier. So these are the three techniques, and this is the four techniques which we want to use, or some uh, like gas or GAIL, ONGC want to use this technique. We have to inject CO2 into the gas hydrate section. Then CO2 will be replaced this methane gas into carbon dioxide gas hydrate. Then we will get the methane gas, and we can extract it out from different another well. So this is the two-way process. We can sequester CO2 also, and we can get methane also. And this is the only that how much means 1200 600 meter depth is required. It is only doing that only. So this is the most prominent example in which we can forcefully apply carbon dioxide. So carbon dioxide also sequester, and we will get the nature gas. Now, so we all know that nature gas is there, but how for developing the technology we have to do research, and for research I saw the actual gas idea from under the sea also, and some from the ONGC we got some sample of it, but it is very much cost effective for this because doing going into the sea and taking the sample out of it and do the research on it, it requires so much amount of money, thousands of crores are required. So what we do, so we can we know that gas hydrate will be formed at high pressure and low temperature, so we can make gas hydrate in our lab also. How? This is one reactor, or you can say as a crystallizer, because it will convert gas into crystal form or solid form. Then you have to add gas into it, so at high pressure, so you have to pressurize the gas into it, you have to add water into it, and after that you have to lower down the temperature by using water bath or chiller. If you lower down the temperature and apply the high pressure, then this is converted into the gas hydrate, which we can make in the lab. And after that you can take it the sample out of it, you can characterize it, you can do the research, you can develop the technology out of it. For temperature and pressure measurement, you can have one data acquisition system which consists every second data of this reactor, and we can show it into the PC, and we can after we can do calculation out of it. So this is one way, and this is the this is the picture. In this picture you can see that we employ one camera into the reactor and take some pictures out of it. I will start the it took picture out of every 20 seconds. If I will start that you can see that how this is the water only, water and gas mixture only, how nature gas will gas hydrate will be formed out of it. I will start the present, I will start the slideshow like this. You can see that as soon as the seconds will be going on, solid crystal like structure will be made. This is a real picture of it. So you can see at the end at the end of 1200 seconds, this is the gas hydrate. So this is done in our lab, so for the understanding purpose. Okay, so you can see that how we will make gas hydrate in the lab. So this is a gas phase and aqueous phase which we have. if we apply the pressure, so it takes some time. After some time it will increase. This is the gas uptake, so it gas will be go into the aqueous phase and it will convert into the gas hydrate. And as soon as, here you can see that this is the before nucleation, means this is only gas and aqueous only. At the time of nucleation, you see the red line is showing indicate the temperature. It is you, if you see that there is a sudden change in temperature, because gas hydrate formation is a exothermic process. So here it is some amount of heat will be released. After that, temperature will be constant again. So after that, liquid and gas will be combined with each other and made gas hydrate. But after some time, you can see that on the surface of liquid, all gas hydrate will be formed. Then more gas will be not penetrated into it. So after some time, there is a mass transfer resistance. Then we cannot form more gas hydrate out of it. So this is one resistance we have to work on it. Okay, so this is this is the reactor which we use. There are so many facilities, but this is one out of it. In here you can see this is the main reactor. In this reactor we fed. Actually, it is used for subsea environment. We have to understand kinetics in subsea environment. So we will fill the sand into this reactor. After this is the supply vessel. In supply vessel, we add gas, we add sand and water into it, and we add gas into it and maintain the lower temperature. You can see the water droplets which will condense out outer surface of it. So we can feed gas into it in this reactor. In this reactor we already fed sand also. So it is same like a marine environment. How marine environment gas hydrate form, it is the same environment we can mimic in our lab also. And this is the so we will form the gas hydrate out of it. And this vessel we can store hot water. So after once gas hydrate will be formed, then we will send a hot water into it. So like thermal stimulation, we will separate gas and water from gas hydrate, and then gas will be stored into this. So this is the one step of technology development of gas hydrate production. Sorry, natural gas production from gas hydrate. So here you can see that there are so many sensors over there. Here you also see that there is a laptop, a computer, and so many systems over there, so many panels over there. So wait, so we can actually get the data of each and every second. So this is one of the facility which we have. Now challenges in lab scale, we have some challenges because slow rate of hydrate formation over there. For 2 days, 3 days, we will able to form little amount of hydrate, 40-50% out of all the gas. And after that, I told you that there is mass transfer resistance over there. So you cannot able to form more hydrate because whole surface will be acquired by this crystal only. So what are the solutions for this? Basically, three solutions are available in this research area. So one is a thermodynamic promoter. We have to add some chemicals like tetrahydrofuran or TBAB. What they do? They shift the hydrate phase stability curve to the higher temperature and lower pressure. Means if you can able to make hydrate at 60 bar and 273 Kelvin, then you, if with the help of THF, you can make hydrate 298 Kelvin also, and below 30-40 bar. So you will reduce the pressure and higher the temperature. And the second is that we can add surfactant. Surfactant, you lower down the surface tension, and we can, after that, mass transfer resistance will be lower down, and we can able to form more gas hydrate out of it. And we can change the reactor design. So I just want to, this is the last part, I just want to talk you with one such application. This is a surfactant solution out of it. As you know that SDS is a one surfactant which we use for gas and oil production also. So methane and water is there. So you can consider that you can, if you add SDS into it, then it will facilitate the surface and we will produce more gas hydrate. So here you can see that if we use SDS and then pure water only, then we will make the gas hydrate, we will consume more gas into the gas hydrate. Like here you can at 0.5 you only get 2 millimoles of gas, but here you can achieve 15 millimoles. And this is how you can enhance the capacity of increasing gas hydrate storage. But there is some problem. If you use surfactants, then there will be a forming will be there. So you can see that this is forming over there. So how can we reduce the forming? This is a picture of our lab. So we will develop some chemicals in there. The chemicals are used for reducing the forming. We name them anti-forming agent. These are all published research. So if we add some anti-forming agent to this, then forming will be rolled down. As you can see over there here that this is so much amount of forming with only surfactant. If we add some anti-forming agent with different concentration, then forming will be lower down. And here you can also see that if we use the different types of concentration, then forming will be over down, as well as gas uptake will be also more, will be more. So this is one example. And there is a future study which is taking place in IIT Madras, that we can form a nanoparticle from iron, ferrous and ferric iron salt. We will form the nanoparticle, and from on that nanoparticle, if we add surfactant, or we can add surfactant in that nanoparticle, as and whatever the final product which we get, which is known as a nanohybrid, if we use them, then you can see over that gas hydrate will be that you can see over here in this graph, that it will take higher amount of gas hydrate than any of the other combination. If we go for a nanoparticle of this, so surfactant coated iron nanoparticle, then we will enhance the gas storage capacity of gas hydrate. These are the sample of this research. Now this is the last slide of my presentation. Means not the last slide, but this is the most important last slide, that economic evolution of gas hydrate technology. You all know that coal bed methane is there. What is the production rate of it? This 500 MSCF, million standard cubic foot per day. For shale gas is 500 to 3,500. For conventional gas and oil, which we use now, which is 90,000 and 1 lakh. If we develop the gas hydrate modeling offshore, then it is go for 5,000 to 15,000. We will extract the 5,000 MSCF per day to 15,000 MSCF per day of natural gas out of it, if we go for a gas hydrate modeling. Now, what is the cost of making the well cost of it? Digging, how much amount of money is needed for digging that well? So for conventional, we have to 15,000 US dollar. 15,000 multiplied by 1,000 US dollar, and 1 lakh. If we go for a gas hydrate, then our well can be, we can dug in 20,000, greater than 20,000 into 1,000 US dollar. So it is also lower down, but our production is also lower down. So in future, we will develop the technology, so these will be lower down or this will be higher down. So we can shift into the gas hydrate technology. So this is one reactor which just we made with the help of Gas Authority India Limited. In this reactor, we will same thing we will do. We will do add sand and water gas, and we will form the gas hydrate. Now this is the last thing. I want to acknowledge all the stakeholders for this. These are all the professors from Rajnish Kumar IIT Madras, NUS Singapore, from Dr. Praveen from NUS, Dr. Ashish from Australia, University of Western Australia, and Dr. Omkar. They are the backbone of this research. We have our funding partners also, NUS Western Australia, Gale Authority, DST, and NCL. So I want to thank you all with this, and that is a pleasure talking to all you guys. And if you have any question, then you can ask me. And thank you for listening me and bearing me for 1 hour. Okay, thanks a lot.
Okay, so there are some questions from student. First question is, what is the future of natural gas hydrate exploration in India?
Okay, so if you talk about the natural gas hydrate, then NGHP 1 is going 2006 to 16. In that, ONGC was invested heavily. So now NGHP 2 is also going on, but Indian government took one decision that they because we don't have much money. Everyone knows that Canada, America have so much money, Japan has so much money, even China has money to do that thing, but we don't have money. So we will collaborate with each other countries. Like Canada, we have collaboration, and USA we have collaboration. We will do research with them, and we will also able to produce gas hydrate from our side with the help of Japan and Canada mostly. This is the thing.
Okay. Second question is future scope of natural gas storage in terms of gas hydrate in India.
Okay, so I told you that now we have natural gas from Alaska majorly. So it will Alaska and Qatar. So it is come into the liquefied natural gas, but liquefaction needs so much amount of money. So we are doing some research that how can we go for the gas side. So there is one project, and most probably we will able to do in future that uh, in from Alaska, US, US will send us the gas hydrate in the nature gas in the form of gas hydrate, and then whatever the water will come with that, so we will extract the gas out of it, and we use that water to uh, sequestration of carbon. So this is the Exxon Mobil project which is going on with Indian government. So in future we will use natural gas hydrate as a transportation medium rather than liquefaction of natural gas.
Okay. Okay, I would like to thank you, sir, for your valuable time, and I look forward to our next meeting. Thank you. Thank you again.
Thank you, Parur University for giving me an opportunity. Thanks.
Okay.